Welcome to today's topic of breadth-first search. BFS is a graph traversal algorithm for visiting or exploring nodes in a graph level by level. It starts at the source node, visits all of its immediate neighbors first, then moves on to the neighbor's neighbor, and so on. So to manage the traversal process, BFS uses a queue data structure that follows the first in, first out rule, meaning the node added first is processed first. This helps us keep track of what to visit next and in what order. And BFS can find the shortest path in an unweighted graph by tracking where each node was discovered from, using a parent map or predecessor map. So to reconstruct the path, we simply trace backward from the target node through this map. And now let's walk through an example of how BFS traverses in a graph. The idea is to explore the graph level by level, starting from a given node and moving to its next level, and so on. So in this case, we will start at node A. First, we add A to the queue, and once a node is added to the queue, we will mark it as visited. An arrow points to A here means it's the current node we are working on. We will explore A's unvisited neighbors, which are B and C. We add both to the queue and mark them as visited right away. And here we added B before C, assuming we follow the alphabetical order. And now A has no more neighbors to explore, so we will dequeue A, and we will add A to our output. So the output here represents the order of traversal. A is now fully processed, and our current node becomes B, because B is next up in the line in the queue. So we look at all of B's unvisited neighbors. In this case, B only connects to A, which we've already marked as visited. So there's no new node to add to the queue. We can dequeue B and add to our output. And now we move on to C, which is next in the queue. So C has three neighbors, A, D, and E. A is already visited, but D and E are not yet visited. So we enqueue them, then mark them as visited. So once that's done, we will dequeue C and add it to the output. Right, and next, we process D, which is now at the front of the queue. So D has two neighbors, C and J. Again, C is already visited, but J is not. So we will enqueue J and mark it as visited. So now we can dequeue D and add it to the output as well. Next is E. Its neighbor already visited, so we will dequeue it and add it to the output. Then we reach J, and same thing, no new nodes to add, so we will dequeue J and finish the traversal. So at this point, the queue is empty and the traversal is complete. And the final BFS traversal order is A, B, C, D, E, J. Now that we've completed the traversal, let's see how this same process can help us find the shortest path from A to J. So to reconstruct the path from A to J, we simply trace back through the path of discovery. So in our case, J was discovered while we were processing D. So J's parent node is D. And similarly, D was discovered from C and C was discovered from A. So if we trace that back, we get JDCA. And if we reverse that path, we will get shortest path from A to J, which is ACDJ. And this is one of the most useful features of BFS, can help us find the shortest path between two nodes in an unweighted graph. And now let's look at how this translates into code. So we begin by creating an empty queue and a visited set. We enqueue the start node and mark it as visited. Then we will enter a loop. As long as the queue isn't empty, we dequeue the front node, process it, and check all its neighbors. So for each unvisited neighbor, we add it to the queue and mark it as visited right away, so we don't visit the same node again later. And this will continue until the queue is empty, which means we've already explored everything reachable from the starting point. So by reachable, we mean like all the nodes that can be connected to the start node by some path through the graph. And here are some additional BFS considerations. BFS works the same way on directed and undirected graph, but in directed graphs, we are only going to follow the edge direction during traversal. And disconnected graph. So if the graph has multiple disconnected components, BFS will only visit nodes in the component that contains the start node. So if we want to visit the entire graph, we need to run BFS on each unvisited node. Cycles in graphs. So we use a visited set to ensure each node is processed only once, and making sure the algorithm is correct and efficient. And lastly, weighted graphs. So BFS assumes all edges are equal. If the weight of the edges matters, BFS no longer guarantee the best path. So in that case, we can use algorithms like Dijkstra's or finding the shortest or cheapest path.